So using this as Qz02, call it systems of units and conversions. We are talking about systems of units, which in our case is the English and the metric. Metric systems. And in defining a system of units, three things are absolutely necessary. Define the quantity, standardize, and make comparisons so that it will make sense. It's a descriptive aspect of measurement. So it's creating a system is define, standardize, and compare. So that's the essence of science anyway. So, you know, if I said 3 miles, everybody would be kind of on the same page relative to 1 foot, which is the standard in English. So that's what we're getting to. So your English and metric standards will define what the fundamental units. Length, weight, time, lumens, whatever you're putting into your standard. Standardize would be the accepted dimensions. And of course the comparisons is self-explanatory, so that you can have a relative idea of how one system compares to the other. This is a magnitude comparison as such. And so as we go through, we apply the dimensional analysis procedures to calculate, and I'll get into the quiz here in a second. And as you recall, I divided it into 3 classes: simple, conversions, multiple conversions, and complex conversions. The simple conversions is unit to unit with no variations in it. Multiple conversion deals with squares and cubes. It is a simple conversion, and then square or cube the conversion factor as needed. But do not square or cube the data, because it's already in the square or cube. Complex is mix of fundamental quantities. Today's lab is a density lab, and it's defined as mass per unit volume. Well, mass cannot be converted into a volume. Volume, it can't be converted into mass. So you have to leave them in the dimensions that you were working with. So grams per milliliter, or pounds per gallon, or whatever you're using. Okay. Now, there's nothing magical about this first one. What weight of salt can be found in 50 grams of aqueous solution that is 25% active in the salt? So how many grams of salt in 50 gram sample, and it's 25% active in the salt? Well, it's no big deal. Everybody knows how to take 25% of the 50. Of course, everybody's seen this before, and that's 12.5 grams salt. But what I want you to also keep in mind is that percentage can be used as a conversion factor if you understand what the concept of percentage means. Percent, by definition, is part over the whole or total times 100%. Well, in our case, here, the 25%, I'll bring it down here, 25% salt can be represented as 25 units, weight units, over the total mix. So this is total. I could put mix right here just to emphasize that issue. So it'd be 25 grams salt, 100 grams of solution mix. So in itself, that ratio is a conversion factor, in that if you multiply that 25 grams over 100 grams solution mix, and you have 50 grams of solution, see how that works? Grams of solution will cancel out, and you're left with the units of grams of salt only. So it is in itself a conversion factor. So I wanted to emphasize that for your benefit, and that is a choice in our collection. Okay, we're given a 30-gram sample of sulfur and iron mix. And mix. And was analyzed to find that the mass of sulfur is equal to 17 grams. What's the percent iron in that mixture? Well, again, you're applying the definition of percentage, and would be the mass of iron over the mass of sample, which is the mix, times 100%. Now, we are given the mass of sulfur, so the mass of iron would be the total mix minus the mass of sulfur. This is M for mass. Mix minus the mass of sulfur, and that's 30 minus 17 grams of iron, and that's 13 grams of iron. So applying the percent definition, percent iron, that's an E, believe it or not, is 13 grams over 30 grams of the mix times 100%, and I got 43.3% by weight. So it means it was calculated based on a weight-weight ratio. And we're looking at B choice in that collection. Okay, a compound was found to be 25 parts per million in the atmosphere. Look like a 5. And that is represented in a percentage. Would be what? So the issue in working with parts per million, parts per billion, or those kind of dimensions is that you are able to interpret what ppm means and then convert it to the desired dimension. You could use ppm to ppb or whatever. And so 25 parts per million is equal to 25 units, parts, per million parts of mix, 10 to the 6 parts atmospheric mix or whatever. And if you're going to percentage, just simply multiply by 100. So in this case, it would reduce to 0.0025%, well, excuse me, yeah, percent based on a weight-weight ratio. Okay, that is C choice in that one. Now, if you wanted to go to parts per billion, it would be the same issue. 25 parts per 10 to the 6 parts times 10 to the, ninth. And then you could tag that with ppb if you needed to go to that dimension. So these are pretty straightforward once you see how they are applied relative to the definition of whatever you're trying to convert. Here's one. The concentration of CO2 in the atmosphere was measured to be 0.0387%. Percent by weight. That equals how many parts per million in that? So it's the same issue. Define what percentage means and then times a million. So the parts per million CO2 is equal to 0.0387 parts CO2 over the 10 to the 6, no, you're given a percentage, I'm sorry, over 100 parts mix, or the atmospheric mix. So those will cancel out and multiply times 10 to the 6, and you'll have it in parts per million. And so I got 378 parts per million in that problem. That would be B choice, and you can go parts per million to percentage or to parts per billion. So that is quite frequently used in the scientific community. Yes, you need to learn those temperature conversion formulas. If you can't derive them, then certainly learn them. Degrees Fahrenheit from Celsius is 9/5 degrees C plus 32 degrees Celsius is 5/9, but you have to put this term in parentheses, degrees Fahrenheit minus 32. C looks like a parenthesis. I always remember it that way, so that's one that has parentheses. F doesn't, so it doesn't have the parentheses in it. And Kelvin, notice it does not have a little degree mark. It's just K, and it's degrees C, whatever it is, plus 273. So you do need to learn those for not just the next test, but for many applications, especially in gas laws, as you may remember. Okay, so if we're given 77 degrees C, convert that to 77 Fahrenheit, degrees Celsius. So the degrees Celsius would be 5/9 degrees F minus 32, and that would be 5/9 77 minus 32, and we'll tag that with the degrees Celsius, and I get 25 degrees Celsius. And so move that down a little bit. C choice in that one. So please do what you need. There's also conversions in energy. The relationship that we use as a base standard is the joule to the calorie, or the calorie back to the joule. One scientific calorie is 4.184 joules. And the joule is derived from definition of work, or work energy. You can go back in the notes and look that up, so if you need to. I won't make a big issue out of that. But it's a complex unit, kilogram meter squared over second squared is the joule. Just as a footnote to, it came out of the definition of work, force times distance.